This meeting is being recorded.
In this next section of chapter 14 on chemical kinetics, we're going to take a look here how temperature and rate are related. So in general, you can assume that as temperature increases, reaction rates will also increase. So again, that's just a general rule of thumb. But the reasoning for this could be due to the rate constant K being temperature dependent. And we can see over here that there are a variety of temperatures along the x-axis, and we can see how K really exponentially grows as we increase temperature. So this is, again, due to the collision model, which states that in a chemical reaction, bonds are broken when two reactants collide, and then new bonds are formed. So we can see down here that before a collision, we have these two different molecules, this one that has the green end here, and then this one also oriented with the green side of the molecule pointing towards the other green atom there. So when they collide, if they are in a proper orientation, a reaction will occur. So that's what we see here. We see this new product formed. These reactants collided with the correct orientation and also the right amount of energy. So specifically what that's called is our activation energy. So a short definition of activation energy is just the minimum amount of energy that is required for a reaction to occur. So again, that is your activation energy. And if we could relate this to this mini golf hole shown over here, there's a certain amount of energy, and that's represented here by the amount of energy provided in this golf swing here to get that ball to go over this hill. So when we depict a reaction in a reaction diagram, generally we use a similar depiction showing the activation energy that's required to lift our reactant at this lower energy, this lower potential energy shown down here on the left. So that has to be raised to the right at energy, which is shown up top here at the point which is called the transition state. So we can say that's the peak of our diagram here. And at that peak, we have what's called the activated complex. So this is the species that's present at the transition state. So again, we see this depiction of this energy diagram here showing our reactants over here on the left, and then our products shown down here rather on the right. We see different states of transition as the energy increases, and then we finally have our activated complex at the peak, and then finally our product down here on the right. So this is this reaction up top here, this isomerization reaction, where this compound just rearranges. And this is the corresponding energy for that reaction to take place. So once again, we have this activation energy, which is commonly abbreviated E sub A, and that's our energy barrier to go from reactant to product. And depending on the size of this, the magnitude of this activation energy, we can generalize again that the lower the value, so the lower activation energy, the higher the rate of reaction, the faster the reaction. So we can also look at something called the Maxwell-Boltzmann distributions. They show us the area below the curve represents the number of molecules in a sample. So depending on temperature, we see two different curves here. We see the blue curve at a lower temperature, and then the red curve, a higher temperature here. So at the higher temperature, we see this activation energy barrier here, this minimum energy requirement here for the reaction to occur is that red line that I just indicated there. We see the number of molecules at a higher temperature. There's more of those, right? There's a higher number in that under that red curve. So we can then extrapolate from this that there's a larger number of molecules at the right amount of activation energy at a higher temperature. So we can relate this through what's called the Arrhenius equation, and that's what is shown over here. We have the activation energy that we just discussed. We have our K, our rate constant. This A here, this is referred to as a frequency factor. We will not do any calculations with this, so you will not see how this is represented, but it just tells you the likelihood of collisions that would occur with the proper orientation, of course. So we need to always consider collisions with proper orientation and energy. And then we know R, the gas constant. This is now the value given in joules, so 8.314 joules per mole Kelvin, and then of course temperature in Kelvin here. So if we were to take this equation and integrate it on both sides, take the natural log on both sides, we would get this form here where this frequency factor does not become important in our calculations. And eventually, we could combine two relationships of rate laws and temperatures for two different equations, and the activation energy being known, and this constant R always being known. If we have at least 4 out of the 5 variables down here, so 4 out of 5 variables, you can solve for the remaining. So that's an important equation. This one's shown down here. That form of the Arrhenius equation, again, which is linking together two different reaction temperatures. So we have our rate constant K1 is associated with T1, and like so, K2 with T2. But we know that depending on the reaction, it still will have the same activation energy that will be constant. But the way that we can think about this equation here is as a linear relationship where our natural log of K is our Y, and our M, if you will, our slope is going to be negative EA over R. And then our X is actually the 1 over T value. So that's where we can get this linear relationship and this actual display over here on the left. So in the next video, we'll take a look at sample exercise 11.